Hi everyone, welcome to GenAI Mastery. This is module 2. Here we will be learning about RAG systems, the basics of RAG such as embeddings, similarity search, and our end goal will be to create a complete RAG pipeline. Now before proceeding to what is RAG, let's talk about why do we need RAG. Now let's say we have the LLM, and LLMs are large language models which are trained heavily on the static kind of data. Now, if we ask something to LLM such as what's our company's vacation policy for 2024, it won't be able to give you the correct output for this question as it does not have the company related context. It can only give you a very generic answer. So here the RAG comes into the picture. Now what is RAG? RAG is basically retrieval augmented generation. As the name suggests, as it first retrieves the context like basically your company's document for vacation, then it augments if this was the question, what is your company's vacation policy, then it whatever context documents it has fetched, it will be attached with the user's query, and then it will be sent to LLM where it will generate the final answer. So this is the complete RAG pipeline as the name suggests. Now moving problem to what RAG solves. LLM is trained on static knowledge, which we have already discussed. There is no private data access for the company related or any internal documents. It can also hallucinate as it does not have the correct context, and no real-time update in the sense that once the language model is trained with static data, it does not get updated with the live real-time data. Now, if we thought about how RAG transform the AI responses, there are some traditional LLM approach. As we discussed, traditional LLM only relied on the closed book approach in the sense that it relies only on the training data. There is no pre-training knowledge. It can hallucinate with the missing information as well as it does not have access to the real-time or private data. But with RAG, we can retrieve the context. We can also, along with the prompt, we can send this context as a prompt. It can be based on the actual documents which company have, and then it can be verifiable as well as cite sources. So this is how RAG works. And the first phase of RAG is like, for example, real world example. Without RAG, if we ask that question to LLM, then LLM can reply with I don't have access to your company specific policies or some generic answer. But with RAG, it can actually give you the correct answer because this time it has the context of the company's policy documents. Moving forward, now what is the high level architecture of RAG? So RAG consists of two main components. One is the retrieval system, second is the generation system. The retrieval system basically have two parts where how do we store the knowledge base and how do we retrieve that knowledge base based on the user's query. Now next is the generation system where how do we proceed with attaching the context with the prompt of the user and send the response to large language model which will give you the final answer. So if we proceed forward with the RAG pipeline, the first one is like first we load the documents from various sources. It can be PDF, it can be web pages, it can be databases. We need to convert them, we need to process them, and we need to chunk them, and then we need to convert them into embeddings. Now what is embedding? We will be double clicking on this as well as moving forward. But once the data is converted into embeddings, we will store these embeddings into vector database. Vector storage. Now what is vector database? We will again be clicking and moving forward in this video. Now once the data is stored into vector database, we will fetch this context documents from this vector storage, and then once the user queries, based on the user query, we will be fetching the data from vector storage like the relevant documents, relevant context, and then sending the complete prompt as well as the documents to the LLM so that the LLM can answer confidently based on the company's valuation or vacation documents. So few terms such as what is embedding, now what is vector storage, we need to think about this or we need to learn about this. So moving forward, we will be learning about the embeddings. Now what are embeddings? Let's say we have some document and it was a very big document. We divided the document into small chunks. Now we need to convert these chunks into embeddings. Embeddings we can also call vectors, which are basically mathematical representation of the meaning of the word. Let's say we have dog. Once we feed this dog word into an embedding model, the output of that embedding model or embed input API will be a vector representation of dog. which can be, if in simple example, if we say the vector outputs or is of 2dd. So for example, if we think of some word, let's say dog. Dog can be converted by a embedding model into 0.8, 0.2. This model only outputs in 2D. Now a puppy, which is also very similar to dog, can give you an embedding of 0.7, 0.3. This is just an example. The real world embedding models outputs in 768, more than 768 dimensions. There are various types of models available, various types of libraries available. Now the more the complex, or more the complex embedding, more the number of embeddings, more the number of dimensions required to store it. And let's say car is very different from dog, so the embedding will be very different and it will be very far from dog. The dog was 0.8, 0.2, and car, we will see a very live example how the embeddings are generated moving forward. And let's say vehicle is also very similar to car, so it might be, the embedding might be similar. So as we think, like, they capture the meaning. Embeddings are just a numerical representation which capture the meaning of the actual words or text. It can be images, it can be documents, it can be anything, but they are actually the coordinates in a high dimensional space. And if two words are very similar, two texts are very similar, two documents are very similar, while after converting to embeddings, they will be stored very close to each other. So this is the embeddings. Now in traditional search, what we do is, like, let's say we have 10 documents and we want to search for some word in those documents. In traditional searches, the keywords will be exactly matched. And let's say if we asked for car and the document, some document have the keyword automobile, but it won't be matched because there was no semantic meaning involved in it. It was just exact keyword search. Car was present, then the document would have came. Otherwise, the document will never come. But here in RAG, we think about semantic searches. Now, semantic understands the concept as well as the context. So, if we say car, if we say vehicle, if we say automobile, all of them are kind of similar kind of things. So, once if we search for a document or a word related to car, the word, that context or that document will be arriving. It has a human like understanding, as we see. So, for an example, if I say I need help with Python loops, in normal traditional search, it will think of words as I need help with Python loops. So if some document have these words Python loops, it might give you an output. But if it does not have it, it won't give it. But in semantic search, it will think about iterations, for loops, while loops, list comprehensions. If any document, if does not have the word loops, it can might be the output, because it might be thinking, it might be meaning of that words Python and loops might be available in the document. So now there can be various types of embeddings. As we thought, the input can be text inputs, it can be documents, it can be sentences, it can be images, it can be audio, it can be videos. Everything will be converted into embeddings, and embeddings, as we thought, they are called vectors, which are the mathematical or numerical representations on which captures the meaning of actual word, sentence, document. We will be taking a very simple example where we will be dealing with sentences. So our first embedding, this is the code example given, the same code I have used in my Python project. If you copy from here, or if you directly, I will share the code with you, or you can directly refer it from here. So for example, here as we see, right, for example, I love programming in Python is the text. Now we are using, for this example, we are using sentence transformer, one of the library, static library, which we will be using, and the model is all MPNet base v2 to convert the text into an embedding. For example, the text is I love programming in Python. Here we pass this text inside the get embedding function, which will convert, encode this text and return as a list, that will be the vector for which. So for example, if we print the text, it is I love programming in Python, and the length of embedding, this model is using 768 dimensions. Initially we learned about 2 dimension, but in real life the dimensions of every word, every sentence will be very high, so that it actually captures the real meaning, and closely related sentences are stored together and different meaning sentences are stored differently. Now the first 5 values here we are printing, and these are in decimal numbers. Now moving towards similarity. Let's say we have few sentences. I love programming in Python. Python programming is my passion. So if you can see clearly, right, a human understands that text 1 and text 2 are very similar. But text 3, I enjoy cooking Italian food, is very different from text 1 and text 2. So if we convert the embeddings of all these three and we find the cosine similarity, I will come towards what is cosine similarity, but if we find the similarity between embedding 1 and embedding 2 and print their values, we can get that the text 1 and text 2, the point values is 0.850, and the text 1 and text 3, which are not very similar, we 0.360. If the value comes close to 1, that means they are very high similar, and if the value comes close to 0, that means they are less similar. So before moving forward, yeah, this is the example of documents. We can have multiple documents, and if we find, let's say if the query was what programming language is good for AI, these were the already existing ones. Human can understand that okay, this is the one, but human will not be able to understand if the documents are very big in sizes, and if the document size exceeds 10,000, 10 lakh kbs of data, gbs of data, mbs of data, then it will also be difficult for human to find the actual AI like basic concept which can be fit to the LLM part. So moving forward, we can try this example. I'll show you a quick example in Python. So this is the embedding generation code. I will share this file. Let's say we have something like the same example, and I have ran this project using the Python command, normal Python command. So let's say we have this model is loaded. Now if we have I love programming in Python, we converted it and we printed the first 10 values. This is the embedding which we get. Now if for multiple things, if we convert, again these are the five sentences which are these, like these are the 5 sentences. I love programming in Python. Python programming is my passion. I enjoy cooking Italian food. If all these are converted into dimensions, embeddings, these are the dimensions. Now if we find the cosine similarity between them, as you can see text 1 and text 2, which are actually very similar, Python it has 0.8503. But if you see text 1 and text 3, I enjoy cooking Italian food and Python programming is very kind of different, but there are keywords such as I love, I enjoy, so it has some kind of similarity, 0.4610. But then machine learning is fascinating. Now this one and the first one, I love programming in Python, or yeah, one text 1 to text 5, sorry, my bad, cooking pasta with fresh herbs and I love programming, there is very less similarity between them, and hence the number is 0.397. Similarly like this, now text 4 and text 5, if we see machine learning and fresh herbs cooking pasta, there is no similarity between them, the model gives us a negative value. So these are the various examples. Now it is actually capturing the meaning, and when we are finding the cosine similarity between them, the cosine similarity is just that we get the vectors for both of these and multiply them, we get a dot product. This is a mathematical formula which we use normally in this, and to find the similarity between two vectors, whether the vectors are close to each other or not, and then we normalize the vector 1 and vector 2 and then divide the dot product with the multiplication of normalized values of 1 and 2. This is a mathematical formula which we use here. Now similarly, if let's say we have multiple documents and we need to find for a query of user, let's say the query was something like generate what programming language is good for AI. We know out of these 6 documents, some things will be matching with AI, such as machine learning algorithms is one, deep learning neural networks might be another approach, or data analysis using Python pandas. Now depending on how many documents we need, we can actually think for something like this. So let's take an example. What programming language is good for AI, and let's say we find the top 3 based on the similarity with everything. We got to know, okay, yeah, these are the similarities and these are the top 3 similarities. There will be always some similarity between two documents, since these are characters, alphabets, there will be some similarity, there will be some meaning which we can say are similar. But for example, now again, how to make delicious Italian food, there were 3 documents: Italian cooking, traditional Italian recipes, and then this cuisine with olive oil. There was some kind of similarity. So yeah, as this was highly similar, the value is 0.7182. Similarly, these were the queries. So now, best practices for data analysis. Again, data analysis, there were some documents which were related to data analysis. Machine learning is also somewhat related to data learning. and then there was one document which was dealing with data science and machine learning. So again, this is the case. So these are the embedding examples. I hope you would have understand what is embeddings and how embeddings help in capturing the meaning of a sentence in mathematical format. And similarly, now the next time where this came into picture, we thought that when something is being asked to LLM, we will be using this embedding model. Like we would have got the company's document, we have converted those documents into chunks, and using embedding models we would have converted those like these documents into vectors, and then we would have stored all these things into a DB. Like here we have very limited example, like only there were 6 7 documents, so we were able to store them in memory and we were able to find them one by one. But in real life we will have lakhs of documents, GBs of data, and if we store everything in memory it will be very slow, the system will become very slow. So moving forward, we have already understood like what is similarity search. Now, as we were thinking, like if there are 10,000 documents, 1 lakh documents, 10,000 documents in real life example, if we see, and if we see the memory usage, like if there are the document size is less, we would, yeah, store in memory and can use it. But if the size of the documents increase, we would need some database. Now, as the output of the embedding models were vector, the mathematical representation of the meaning, we need a database which works on vector. So the solution directly comes to vector database. Vector databases are databases which are designed for this purpose only, like they can store, index, as well as we can search if we need. As we were thinking about examples, right, we will know what is the programming language used for AI. This was the query, we needed to find the documents which were relevant to this query. So these are the embeddings which we need to fetch from the vector database, and they are optimized, these databases are optimized for these kind of similarity search, semantic searches. So traditional approaches, if we think if we store everything in memory, we will be taking order of n time complexity, like we will be going towards every document and seeing whether this matches or not. But in vector databases we can use indexing, we can use log n time complexity, as well as since these are databases, these are optimized for this only, they scales to millions of vectors. Now there are various types of vector databases available in the market. For this learning purpose we will be using Milbus. You can read about them here in this website. I will be sharing the link of this website and this page. Like if for your project production wise or for other use cases you will be using some other DB, but for this learning purpose I am using an open source highly scalable Milbus vector DB for this example. So now as we have know, like once we got the documents, let's say we have 10,000 documents and we need to convert these documents. Now embedding models take a document as an input. Document may be very big in size, we need to convert those documents into small chunks. I'll come forward when we take a real life example of the RAG system, like how do we divide a document into chunks. But let's say we have chunks of data and now we need to convert these chunks of data into embeddings. So we will be using those APIs, and once we have the embeddings we need to store them to DB. So I will share you the code, but for example we will be connecting to the Milbus DB, and like let's say for the very first time in our DB, if we don't have a collection, we will be creating the collection. The collection is similar kind of, we can think of as an SQL kind of thing, where we have multiple columns. So this field schema defines one column which is like an ID, and here we are auto generating it to true. Next is like the embedding, the actual embedding which we want to store in DB, and the next is like the actual chunk of the data which was the real value of the embedding. We won't be able to understand from the embedding like what embedding actually was there. So based on the similarity, once embedding matching is done, we will return the chunk. So here we are creating the index for this table. So once these fields are defined, we will be creating a schema from these fields. We are defining the description of this schema, and here we have created the collection. I'll show you a real life example and a working example of this DB as well. Now here we are creating an index and we know we will be matching with the embedding. So here we are creating an index on the embedding column. And once we have created, here again we are defining like what kind of similarity match we need to perform. So here we are performing the cosine similarity. I'll come up and explain the similarities in more detail later part of the video, but there are multiple types of similarity. There can be cosine similarity, there can be Euclidean similarity, which we usually call it as L2. but this is the way we create the columns. Here we are defining the columns and we have created the columns. Now moving forward, we will be inserting. Now let's say we have a new embedding, we have a new chunk for which the embedding is given. We just get the collection and we just call the collection.insert method, and this will be stored into our DB. Now search embedding, here we have that given that k is equal to 5. So when a query embedding is being given that okay, this is the question which user have given and I need to find relevant context, relevant documents from the DB, I will be passing a value of k. This can be customized. I need k value 5, which means I need 5 documents. So this is the case, and we will be calling the collection dot search. We will be passing the query embedding. What is the machine learning, what is the language used for AI? That will be our question, and here limit we are giving it as k. And we have defined like what kind of similarity search you need to, or semantic search you need to perform. So here we have defined it is the cosine type similarity. So these are the multiple ways which we can do with Milbus. Let me give you a complete example for it. So here is our Milbus client. One second. So this is the Milbus client. That the same code example we are making a connection to our DB. We are creating collection. So if the collection it does not exist, we will be creating the collection here. Once the collection schema is defined, we'll be creating the collection. We will be creating an index. I'll sharing you the code. And once the index is creating, we have a function to just insert the embedding, and then we have a function to get the embedding. This is the three function which we need from DB: inserting the data, getting the data. And if I show you the data will be represented in this format. So the project is running, the DB is connected, and it has three columns. For example, ID is there is an embedding field. This will be of 768 dimension, only two values are being shown, but if I show you the other values it will be present. And then we have the actual chunk. So there is some kind of data which is present. For example, apples is present. These are the values for embedding for the data which is present here on the right side, apples. Similarly, if there are some kind of other data, this is another document. So there was one document which I have used. For example, this samples.txt. This was one document, sample document, and it has a description of apples. I stored this document. First, I converted this document into chunks, and then I converted those chunks into embeddings, and then I inserted those embeddings using the insert embedding function into my DB. And once inserted, everything is available here as embeddings. Now I have created a UI for it. Let's say if I ask anything on vegetables. Right now the DB does not have anything on like vegetables. Everything it has was apples. So if I ask search and the k value, let's say I'm giving it as a 2, search, I need two documents which are related to vegetables, but it could not find anything on vegetables. The things which could find was only apples. Apples was there, it was, and this time this document was inserted twice, so it is giving me the two documents which are very kind similar, but it could not find anything on vegetables. But if I ask about apples, like what are the various kinds of apples or what are apples, it will be giving me. And let's say we increase the value of k to 3. Here if I ask it, it will be giving me the context relevant documents which are very similar to apples. It has given me some documents which has some information on apples, which has some information on apple, which has some information on apple. I can increase the value of k to, let's say, 10. Now it will give me all the 10 documents which are related to apples. Everything is about apples. Since the database does not have any information on vegetables, it won't be able to give it to me. But let's say now I have an endpoint, and let's say if I select a vegetables.txt file and now I open this file, there will be some pre-processing happening, like the document is very big in size, it is being converted into chunks are being converted into embeddings. As soon as I click on the upload button, the file is loaded. This is the process which will be happening, Now it is uploading and it will be updated into done. So as it was, the document was very big in size, it inserted 13 chunks into the DB. If I refresh the DB, right now there are 14 entities, 14 entries, and now there are 27 entities, as you can see. And most probably the vegetables information is now present. So if I ask and think about what are vegetables, and let's say get 5 chunks, it will give me all the information which are related to vegetables. See, now it is vegetables, all these are, all the documents are vegetables. So this is the complete working of RAG system, like not the complete working of RAG system, the complete working of retrieval and uh, how to get the data from DB. So moving forward, I hope you understand this part. There are various advanced Milvus features. Right now I won't explain you all these things. You can come to the website and learn about them. The code and every detail is being present in the website. I will come up in this in the later video explaining all the advanced and optimization tips for DB and everything. Now, since we have learnt about vector databases, how to do the Milbus setup, how to get the system like semantic search architecture and everything, I will move forward to like the end goal, more towards the end goal, like how to build the rack systems. What are the different types of rack systems? And now you would have understand like we are actually close to solve this LLM language problem. Now, if we ask any question to LLM regarding the company's policy vacation policy for 2024, this time, before asking the question, we will first find the company's vacation policy from the chunk of data which we have, from the database which we have. Once we have the relevant chunk of documents which we can provide to LLM along with the user's query, we will get a correct answer. We will get a better answers. So we have understood the RAG, we have understood like what is the, like we have understood how, what is knowledge base, how to get the search engine, and next we will be learning about how to generate the system, like generation system, how large language models work. So we have completed the phase 1, like document ingestion, how to store the data, how to convert or store multiple PDF web pages. We have taken an example of text file, but similar pre-processing and conversion can be happening on PDFs, web pages, and as well as other data. Now we will be doing some text processing if there are some documents or metadata which we don't need to store them into direct databases. We can do that. We can chunk the data if the document size is very big. Once the embedding are generated, those will be converted to vector representations which are embeddings, and then we will store them into vector storage. This was phase 1. Next is how this was working, like when I asked what are vegetables and I click and provide the value of k is equal to 5, and once I click on search, what actually happened, the complete process. So the first was like query analysis. The first API endpoint, that was an API endpoint which receives a user question, what is vegetable or what are vegetables. Now this what are vegetables need to be searched into the vector DB, and we know that vector DB only have information can be searched, like we have created an indexing on embedding, and this is optimized, this is like this DB is optimized for searching via embedding, not via text. Although we have text, but this will not be optimal. We want to do a search on embedding. So first we need to convert what are vegetables into embedding. So first second step is query embedding. We convert the question into a vector locally, like using sentence transformer or using an API. So now once that is converted, we will be doing a similarity search. It can be L2 distance, it can be cosine similarity. Here we have mentioned about L2, but actually we were doing cosine similarity. So once we have the relevant chunks, we will retrieve the chunks. Now along with the user query, we will attach the context as well as some system instructions if we want to do, and we will combine everything, and then we will send all this to LLM. And now LLM will give us an answer, and we will reformat the data and will give it to us. So for example, when the question was what are vegetables, it was being converted into embeddings, it embedding, and then it was searched into our vector DB, and the value was 5, so it gave me 5 context documents. Now, along with the user question like what are vegetables and these 5 documents, everything was being sent to LLM, and the response of LLM came to me was this AI answer: vegetables are essential components of healthy diet, providing vitamins, minerals, and dietary fiber. So this is a human readable format and very good answer, like what of the question what are vegetables. So this is the complete flow. If we would have asked something like, if the document like what are machines, for example, and if I search it, now that there is no data for machines in our documents, there might be something matching with apples or something it matched, but it could not, this is not the correct database for us. So when once our question what are machines is being along with this relevant chunk, which is actually not relevant, it's passed to LLM could identify that I need to answer based on these chunks and I could not find anything related to apples, it would have given a wrong answer, and that's why the AI answer is like I don't know. This is being defined in my code, which I will show you later. That if the answer is not relevant, or if the AI answers like I'm not sure about the answer, the final answer should be I don't know, so that we can be aware that this is actually the AI was not giving me a hallucinated answer. So, for example, like employee, when employee asks whatever is vacation policy, I will give you a detail once again. It will be sent using sentence transformer. We convert into a 768 dimensional vector, and then we get some relevant using the relevance score like what all documents matched. We got the top 3 to 5. We define k is equal to 5. Now once that is done, we combine the user prompt and the context into a prompt and pass it to LLM. Once everything is done, LLM gave us an answer which we show it to user. This is the complete pipeline of RAG which we can see. So this is like, and now basic other details is like we have nav rag. There are various types of rag architecture. This is the nav rag pipeline which we discussed, like users query, then we retrieve the data, then we generate the prompt and give it to LLM. The LLM generates the answer and we get a response which we show it to the user. This is like a simple linear pipeline which is like a basic Q&A system. This is basically used for learning proof of concept, but we have other advanced RAG pipeline as well, on which I will make a different new video. But to give you an idea, we have like optimized multi-stage process where we do a query processing. Once we do the query processing, and it is not a normal retrieval, it is a smart retrieval. We combine the words, we combine the semantic search, then once we get the documents we score them, and if the score are less we make another query to DB. If we get relevant documents again, if not we will again make this query, and now we will, based on the relevant score, we will only feed the top matching documents, not the k, to the context, and then the context optimization is done. We also create a very good optimized prompt to the LLM. This becomes an advanced rank enhanced pipeline, and then we get the enhanced generation output. Now it can also have a modular rag, like we have different components attached. Now instead of milbus db there can be some other kind of db, chroma db or other kind of db which can be used for converting into embeddings. We can have multi models based on the input query of user. We can decide on which embedding model which we need to use. So these kinds of things which we can do. We can have multi-hop rog, self-rag pattern where there are feedback evaluation. Multi-hop rog, if I can see, like it basically follows up queries based on the finding, and then it like this I explained, right? When it is making one round of retrieval, it can make another round of retrieval, multiple rounds of retrieval from the DB to get better chunks of context. Self-rag is something like once it returns the output, it can learn from it itself whether it was a good context or not. If determines that more retrieval is needed, it will again make query to the DB based on the user's query. Hybrid rag can be semantic plus similar kind of search. So every topic needs a complete new video. But these are some advanced rag patterns. For initial phase, we don't need all these things. So we have learned about this document ingestion pipeline. I'll show you in the code about this. So for example, let's say we have main file, we have created a prompt. So there are multiple, this was one endpoint query, another was upload. Let's say we upload a file, we had a new file or new document, Now we document is being chunk. Since it was very big document, chunks are being created. Now for each chunk in chunks, we are creating a get embedding file, like get embedding for that chunk, and now we are inserting all these chunks into it, into the DB. And let's say all the embeddings are being created and inserted into DB, then we return like how many chunks are inserted. Now once the data is inserted, let me double click on every method. We have chunk utils. So here we have defined that overlap, so there can be multiple strategies for chunking. So for example, I think would have defined here embedding basics. One second. I thought I would have defined it. Yes. So chunking strategies deep dive, like we can have fixed size chunking. Something like if a document is of 10,000 words, we can define that okay, every chunk should have 500 or 1,000 characters typically. Or it can have something like semantic chunking. It based on the meaning. Let's say if it has some kind of meaning on this paragraph, let that be one chunk. If it has some other section in the document which has a complete different meaning, and then they can be based on this semantic chunking. Like these are all decided by the models which we are using to convert a normal text into embeddings. So this is another semantic chunking. Third is hierarchical chunking, where we are like converting a document into multiple sections, then multiple paragraph, and then multiple sentence. We maintain all this, and this is very complex chunking. So in this example, I have taken this fixed chunking, where I have defined that I will be using a chunk size of 500 characters. So I get a text which is one of the file, and now I'm creating multiple chunks out of these every 500. There can be overlap, but here I have defined overlap is equal to 0 between chunks. Now once our chunks are created, we return these chunks, and now we are passing all these chunks into this embedding function, where we are using a model of sentence transformer library. Now once the model encodes this text, it returns the embedding. Now once embeddings are returned, we will be storing them into DB. So here is the main file. Once the embeddings, we will be calling this insert embedding methods, which is in the same file milbus. We are getting the collection, and we are inserting these embeddings as well as their chunks. Now once the embeddings are inserted into DB, the part of uploading a document is done. The second part is when the user asks what are vegetables. So again same thing, we have another endpoint for a query. This is the query endpoint. Let's say the query was what are vegetables. We need to convert what are vegetables into embeddings, so we say get embedding on the query. Once the query embeddings are created, we now need to fetch relevant the context or documents from the DB. So we pass the query embedding into search embedding function, which is of milbus, which we have defined. Now query embedding is passed, also whatever k which we have like user taken from this example, but this is actually something which need to fine tune our reg model. So let's say we pass the value of k here. Now search embedding is of milbus client function, which we have defined. Now getting the collection, here we are calling the collection dot search method, and now we are passing the query embedding which we need to pass. Also we are defining that we need to make a similarity search of cosine similarity, and the value of k is limit. This will give us the output of k documents or k embeddings, which we can say. Now we will have chunks. The output field is chunk. We are interested in the chunks of the output, so we get the k. Now this returns from the main file. Now once we have the top chunks, now based on the user query and the top chunks, as I was saying, so based on the top chunks which we get from search embeddings, we create a prompt using the user query as well as the top chunks. We combine both of them into a prompt, and then we make an API call. This you would have learned in module 1. Like I'm using a Gemini API call. Here I am passing whatever is the prompt I get from this build prompt function, combining query and top chunks into this API call, and then whatever is the output of this response, I am showing it to the user. Here, as I mentioned, that I'm just post filtering, I'm just checking if it would have hallucinated, it would have written something like generally, commonly, typically. So here I have done the post filtering on the response, and if there is anything something like generally, commonly, typically, I am returning as I don't know. This means that the LLM was not able to find the relevant context, and hence it could not answer properly based on the relevant chunk. So now the prompt is something like we pass the query and Tom chunks. So here we are defining that you are an AI assistant. This is the prompt which we have defined, like instructions which we have defined. The question was, and we have also answer. We have also given it something like that you are an AI assistant, and based on you answer only on the context documents provided. LLMs are already trained with a huge amounts of data. If you ask something to LLM, they have a tendency to give you an answer. But if you provide them this instruction that do not answer, only answer based on the context documents which I have given it to you, otherwise say like I don't know or don't provide. So in that case, here we have clearly mentioned that if the answer cannot be found in the documents, if the what are machines is not available on apples and vegetables documents, then you must respond with exactly I don't know. So LLM actually reply with I don't know. We have given some instruction like do not use outside knowledge, do not make up or guess answers. We have defined the query, and now the once the query is defined, we in like attach all the context documents into it, and then we have also given like the prompt should be answer here, so that once it answers us to us, it will be like we can make a filtering on answer keyword, and then we can do it here. So once it finds it out, then response.json we are able to find the answer, and we are returning the answer. So when we are returning the answer, we are giving the user query what are the top chunks which we have used to find an answer, and we are returning the answer. So giving you an example, if I ask how are apples cultivated, and let's say if I define the case value 1, like based on one document give me an answer. So there was something related to apples which it could find on cultivation, and here also, since we have asked how are apples cultivated, it could find something on apples, but there was no information it which it could define for cultivation. So hence it says AI can say I don't know for this example. We don't have much information which we have not given for apples to our vector DB. If we would have given, we would have get this information from DB. Also, we can improve prompt, we can find to our model, and we can improve the complete RAG pipeline for this. So this is the basic example which I have explained in this video, like how to add more context documents here, how to like what happens if we add more context, how they are converted into embeddings, how they are stored into DB, and if I query, what happens when I query something, like if how they are converted to embeddings, how the relevant chunks are fetched, how the user query and the relevant chunks are combined, and how they are being sent to LLM to get a perfect answer. Here I have used like the tech stack which I have used is like fast API for this endpoint creation, and which I have defined here, I believe, in the home page. So fast API for creating the APIs, we are using Milvus vector database to store all the embeddings. We have used sentence transformer to create embeddings, which is actually a local embedding model. We don't have used any API call for this. Again, to make LLM calls, we are using Google Gemini LLM. Docker is mainly used. We are using this Milvus DB. So we have locally deployed the Milvus DB. So for that we are using the Docker, and Docker Compose everything about this. I will be sharing everything like all the code related files and the instruction to run and then test everything in a repo, and a readme file will be attached. So I think you will be able to do setup. If there is any problem in the setup, I can help with that. And then yeah, Python is mostly used for this environment. So I believe everything is being completed in the building RAG project pipeline. Here we have defined like what all things are needed, like what process documents, smart search, generate answers. Here we have defined everything in detail also. like which file, like the project files, embedding utils.python file, what does it do, chunk utils.python file, what does it do, milvus client.file, then main.py file, what all documents or what all endpoints do we have. Now how all the components are working together, this I have already explained multiple times. Now here I have defined, yes, like how to get the project. I will be sharing the repo link, everything along with this video. So you need to navigate to the rag project, start the system, how to test the APIs, everything are defined in this complete repo. So I think this will be very helpful. Coming forward, we'll be learning about a lot of details on this advanced AI systems. So this is the second module. Next we will be doing prompt engineering, chatbot creation, AI agents, MCP server, everything in detail. I hope this lesson might be helpful for you. Thank you.